Right. Wow, here we are in, well, no longer so much sunny, not sunny, Australia. It's an amazing trip to get here, I'll say that. How many people are actually from here? Right. Okay, so the rest of you know the experience of getting here, right? It's really awesome. But it's lots of fun. It's like, what an amazing place to be. It's really cool. Okay. jPDM. So what are we doing? Well, this week I came here to do this workshop for the guys here at IMC, and they nicely decided to host this jug meeting, which is really cool. And as for a talk, I was trying to get them to do another talk. They said, no, you want one of these talks. So I said, fine, okay. So what am I doing here? I'm going to introduce to you basically the performance tuning methodology that we use in all of our engagements and for tuning applications. We've worked on things like control planes to trains to submarines to just about banks, everything in between. So I do a lot of performance tuning. Have been doing so since for a long time. I'm not going to say how long. And do performance tuning workshops, and have co-founded this tooling team where what we're trying to do is what I consider to be the next generation of performance tuning tools. So we're trying to make intelligent tools that can actually do the diagnostics themselves. Right. So nice talk. We're going to talk about performance tuning, and I just want to put this up here when I talk about benchmarks, right? I don't know if you can read that. It says, Professor Zapinski proved that the squid is more intelligent than the house cat when posed with puzzles under similar conditions. That describes benchmarking. I know Jonathan was nicely talking about benchmarking in the last session, and we have nice discussions about this when we get together, but anyways, that's it. So take it with a grain of salt. Our typical customer, application isn't performing to project expectations. Sometimes the project's actually been canceled, I kid you not. So they call me in, it's on Friday, I get calls and say, can you be here now because the project, we need some help. And I'm going, yeah, okay, maybe Monday, not weekend. So I come in Monday morning, and then I figure out, yeah, project's either to be canceled, has been canceled, because it's simply not meeting its performance requirements. And, there's all kinds of difficulties because of that. Least of which is, like, you certainly don't want to have bad performing applications when you're dealing with these guys, right? I don't know if you've heard of the Apps for Apes program. But apparently these guys get very upset and they don't react well when your application doesn't perform well. They even have a Tinder app for orangutans, believe it or not. It's swipe left, swipe right. And it's actually quite useful because it helps them to understand potential mates when zoos try to ship these guys across the planet, right? You can imagine, it's like they shipped him. No way, not happening. But anyways, so apparently they get frustrated when apps don't perform well, and they end up breaking these things. Of course, they're much more hardened than this one, but that's, another story. Okay, things don't work well. What happens? Developers get involved. They start looking at things. So yeah, we were talking about strings before, so this is appropriate. Like, ooh, we're using string buffer, so let's change it to string builder, because that's really going to help us. Looks like a database problem, so we need to migrate to, what's your favorite database now? NoSQL, what's that? MongoDB. Sorry, Mongo guys. Hadoop, yeah, there we go. Now we're talking, yeah, okay, Spark, whatever, it's a good, right? And so they make all these changes, and they still have these problems, and it's like, who knows what's going on, right? And then of course the pointy hair people get involved, and what do? They form a tiger team. Isn't that awesome? Have you guys ever been part of a tiger team? Hands up. Oh, they do? Oh, yeah, there you go. So you know the Tiger team, right? So what is a Tiger team? It's a team of specialists in a particular field brought together to work on a specific task, right? Wrong. What is a Tiger team? It's a forum where experts from different disciplines come together to express an opinion that defends their speciality. Am I right? Yeah, there we go. That's exactly what it is. So how do we get around all of this? Well, I've been involved in a few Tiger teams myself, and there's something that annoys everybody. And that's when you come up with a good definitive measure that just blows a hole in everybody's story, right? So solid measurements can really, really turn these exercises around. And really the motto behind these types of exercises is measure, don't guess. And that's what our Java Performance Diagnostic model is designed to do, is to help you get measurements with confidence, to help you to interpret them, to help you understand how you're supposed to progress from the beginning of a performance tuning engagement to the end. And that's really what this model is here, right? So why a model, right? Well, in general, models are nice abstractions of things. They help us to understand the things that are fairly complex. Now, that's the good side of models. Of course, models, by their nature, ignore some complexities, so they're not always perfect. But generally, models are very, very helpful for helping us to understand what's going on, especially in complex systems. Okay, so let's develop a model. So the first question is, where do developers live, right? Well, most developers work here. That's pretty much, that's their life. They're in the code. And, they generally work in this nice virtualized environment, right? So what you call a JVM. So I think these should be elements of our model, right? Application, JVM, sounds pretty good, right? So they're doing this. They're writing software. It's exceptionally abstract. Okay, so that doesn't seem quite right. So what are we missing? Well, we're missing hardware. Well, hardware is real, and hardware comes with the capacities and volumes and throughputs defined by clock speeds, and you have different levels of granularity that things work at. CPUs will work in cache lines. Networks work in MTUs, or packet size, packet payload sizes. Disks work on specific sizes. So all of these components internal just work on specific sized things. And of course, it's clocks and things like that control how fast they can actually function. We have CPUs, numbers of cores, and even you get into number of units in the ALU, right? So quick question here for you. Do you know how many floating point divide units you have in a CPU typically? I'd say an 8-core, like 4-core hyper-threaded. One. Yeah, sorry, these guys know back there. Absolutely, right? So if you're doing a lot of floating point divides, guess what you can quickly do? You can basically get stuck on this component inside the CPU that you're going like, what? Okay. Anyways, that's the whole point. Memory, of course. We have, I got 16 gigabytes in here. It's awesome, right? I wish it was 32, but it is what it is. Disk, the same type of thing. So you can look at these things, you can look at the specs of them, and what they're going to do is they're going to bring some reality to the problem, right? They're defining the capacities, they're defining the real speeds that things can travel at. So I would like hardware to be part of my model, because really performance emerges when abstraction meets reality. And so it seems like I should have the hardware in there. Oh, and this operating system thing? Well, that's really a provisioning system. Like, I don't do anything in the hardware unless I go through the operating system and it provisions that resource to me. And then after that, I can actually use it. Okay. What else do we need? Well, there's absolutely no dynamics in the system, right? So this is like roads with no cars. There's never a traffic jam when you have a road with no cars, right? It's the perfect thing. So we need to add the cars to the system. In this case, I'm going to add the actors, because the actors are going to add the dynamics to the system. Okay? So, and we need the dynamics. So you guys heard a little bit about the JIT from Jonathan in the last thing, and he's basically saying he's making these dynamic optimizations. And there's some things you just can't know in your cubicle. So here's a question, right? Which is faster, bubble sort or quick sort? Depends. Do you know in your cube? Maybe you do, most likely you don't. So if you have to sort things, which one are you going to choose? Quick sort, obviously, right? You know, there's a hint as to, you know, I was hoping everybody said, oh, quick sort's really much, much faster. However, you know, that's the reality of the situation there. Bubble sort, you don't need to go through the setup and tear down operations. You just get on with it. And with the quick sort, you know, you have to do this, you know, setup, tear down type stuff, and consequently, for lower numbers of elements, it's actually slower just because you have to overcome this overhead costs, right? So, and this is a decision you can make dynamically in the runtime. It's like, oh, list 10, okay, bubble it. List, you know, 10 billion, probably quick sort that one. That might be a better choice. So how do we know? Well, sometimes we don't really know until the actors get involved and they basically do something and they say, okay, you know, that's the way it goes. Okay. So let's build up a methodology around this, right, based on the system model. Hypothesis free. We want to be very methodical about it, and we want to be stepwise so that every step is basically advancing us towards whatever the solution is. So it's a very methodical diagnostic process. Okay. What do we have here? So this is how it's basically going to work. So actors are going to drive the application. The application is going to drive down onto the JVM. The JVM is going to drive down on the hardware and start consuming all of the hardware here. Of course, the consumption is going to be limited by some capacity. And really what we want to look for at the end of it is like, what are the hardware consumption patterns? And I'm going to look at these consumption patterns, and I'm going to do analysis on the consumption patterns. I'm going to try to identify first who's the dominating consumer. And what I mean by dominating consumer here is what is the activity inside the hardware that's controlling how the hardware is being utilized. In this case, we'll focus on the CPU to start with, right? So to get that, I'm going to have to look at the hardware counters when the system is under load, and then try to do some analysis on that. Okay, so who are my possible dominating consumers? Well, we have, whoops, some animation in there. Application, JVM, operating system, not actors, right? Our first one is going to be, whoops, things coming off here a bit. Our application, JVM, our system, and we're going to have something down here which I call none, which means there's no dominating consumer of the CPU. And each of these different dominating consumers actually represents a different class of performance problems. And we can get which class of performance problem we're in by examining the hardware counters and doing the analysis on the hardware counters, okay? And this is really what I would call a filter. So we want to take a problem that's really infinitely large and somehow make it small and manageable. So this is what it's going to do. It's going to help us do that. Okay, so how do we get into the analysis? Well, okay, let's introduce a flow chart, right? Flow charts are nice. You like them? Okay, perfect. Okay, so the first question I'm going to ask is the system or kernel time greater than approximately 10% of the user time? Now, I'm going to give you magic numbers that are human memorable. The real numbers are different, and it varies by hardware. We actually have machine learning algorithms that we train to get the real values. And the values can fluctuate around a bit, so we have machine learning that actually helps us do the analysis to get around the variability here. But you know, for a rough rule of thumb, to get a first look at what's going on, we can just use the 10% rule here. So the point is, if we're in this condition here, where the kernel time is basically more than 10% of user time, then you can think of it this way. There's not a lot of activity in my application that's really pushing really hard on the kernel. So in this case, I want to find out, I'm going to declare system to be dominating consumer, and what I want to do is I want to find out how and why my application is pushing so hard on the kernel. So a nice side effect of this methodology is that, and the model, is I actually start getting lists of tools that are going to help me answer the question. In this case, I could use some system profiling tools like netstat, istat, iostat, vmstat, mpstat, who knows, SAR, strace, ptrace, things like that that can actually help me understand what's going on. Okay, so we looked at it, and our system time is low, application time is higher, but maybe it's not that high. Maybe we have a lot of idle. So think of it this way. My users are complaining. I have really poor response times, and my CPUs are idle, or effectively idle. So the question is, what gives with that? So I'd like to investigate why my jobs are not in the CPU, consuming the CPU, because if they're not there, you're not going to be making good forward progress. Okay? So how do we get better CPU saturation? So we're going to ask the question, do we have a thread liveliness issue? And it might be thread starvation, might be thread blockage for congestion for some reason, we don't know why. All we know is that we have that particular issue, and we can generally easily in Java figure this out by just simply doing a thread dump. So far, none of the tools here have been exactly exotic, I would say, right? They're everyday run-of-the-mill tools. We just need to apply them at the right point in time. Okay, say we get really, really good CPU saturation, like 100% or so, or more. And I'm going to go on to the next step. I'm going to ask, is the application memory efficient? Which means I need the GC logs. And I'm going to do an analysis on the GC logs to answer the question, okay, are we memory efficient? And, or is the garbage collector adequately tuned? So if we're not memory efficient, I'm going to do some memory strength reduction in the algorithms. In other words, find allocation hotspots and see if I can break them up. Or if there's an issue with the garbage collector, then I'm going to go and tune the garbage collector. If everything looks good with the garbage collector and the allocation, then I'm going to say the application is at fault here, and I'm going to do some straight up execution profiling to figure out where the call sites, the hotspots are, execution hotspots are in the application. Okay? Does that make sense? Excellent. So if we're going to look at expression of CPU dominance, the stuff on the left is going to be passively dominant. The stuff on the right is going to be aggressively dominant. And what I mean by that is that passively dominant is that it's going to leave the system in a situation where not only is it not using the CPU, it's not going to let anything else use the CPU. And if you try to push pressure on it to use the CPU, you tend to get results that are worse than if you didn't. Whereas aggressively dominant, I think that's quite understandable. It's just I'm using the CPU, so saw it off or bugger off and go someplace else. Okay. In terms of measuring, the red shows up in kernel time, the none shows up in idle time, and these two show up in user time, which is why we need the GC log to tease those two apart. Okay? So this means that if you look at CPU charts, we need to consider all of the colors on the chart, right? And yes, in this world, black is a color. I used to tell my daughters that black wasn't a color, and they were always annoyed at that, but in this case, I have to say black is a color. Okay, and it's just as important as the green color and the red color that typically show up on the charts. Okay, so let's try one. See if you can try it first. Anyone can, I know it's hard on the side to see, but can anyone sort of give a guess at what the dominating consumer might be for this particular system? I'll give you a second. Sorry?
This is Windows 66.
No, this is not Windows. It's a Linux system of some sort. I don't remember. Doesn't really matter. So we can go down the user and the system column here, because this is where our CPU summary is, right? So we have idle time and wait time. And we can look at this and we can say, okay, well, essentially, this is what we call swimming pool chemistry. Do you know this one? It's like how much chlorine do you put in the swimming pool? It's just like, maybe a bit more. Not precise. So divide by 10 is basically strip off the second column and see what it does, right? So it's 1, 1, 1, 1, 1, 1, 1, 1, 1, and this is always greater than 1 for system time, meaning that this is system dominant. Okay? That means that the application is pushing really, really, really hard down onto the operating system, and so we happen to have some other counters here that might help us to understand how the application is pushing down on the hardware. So we can go through that and take a look. For instance, okay, we have a bunch of idle here, and we have a runnable queue over on the other side. So we have threads in the runnable queue wanting the CPU, and we have idle in the CPU. That's generally not a good sign. It could be a sign of some contention on someplace. But more importantly, we have this other column over here, which is like a wait column, wait time column, right? So what's with that? Well, the wait time column is really saying, you know, I have a job, it's in the CPU, and if I context switch that thing out because I'm blocked on I/O or something like that, and then context switch that thing in, then generally the cost for that is going to be like 80,000 clocks in, 80,000 clocks out, meaning I'm going to burn 160,000 clocks, but I know this thing is going to come to me within about 40 to 50,000 clocks. So the optimizers inside the engine are going to say, well, you know what? Rather than doing a full context switch and burning 160,000 clocks to get this guy back in here, why don't we just burn the 40,000, having him spin, doing nothing? Okay? And you can see we're spending a lot of time in here in this particular wait state, and that generally means that we're stuffed up on some sort of disk I/O activity. So I would say the condition of this particular machine, this piece of hardware, is that processes running on it are going to be I/O bound. Okay? Now, the nice thing about this type of analysis is, are we running a Java app here? Maybe. Maybe not. We don't know. Are we running more than one process? 1 process? 10 processes? 100? Don't know. All I know is the condition of this hardware is it's I/O bound, meaning anybody using I/O, disk I/O, on this machine is going to exhibit I/O boundedness in their performance picture. Okay? Because hardware doesn't care about processes. Hardware doesn't care about threads. Hardware doesn't care about any of these abstractions that we use to help organize our thoughts. It just flows. Well, it's a bit of a lie, but it's mostly true. Okay?
Each row is the right process?
No, I should explain the output. Sorry, this is VMstat output, and I'm basically printing a line here every n seconds. Typically, I do it every 5 seconds. And I just print out the value of the hardware counter, so the counter is kept by the performance units inside the operating system, right? So if I look at the CPU, this should add up to 100, these 4 columns here, right? Because that's a profile of what the threads are doing here, okay? And we have other things here. We have context switching rates here, right? So there's an excessive amount of context switching happening on this particular box. Here's our block out activity. So we're writing a lot of data out here. We have a runnable queue, a block queue over here. So you can see that we're getting backed up on I/O enough that it is deciding that it needs to take jobs out of the CPU because they're in this block condition. And here we have some memory, how much swap, how much free, how much buffer, how much cache. So buffers for I/O buffers, cache is going to be for shared text and things like that. So this is like how much is going to be consumed. So you, on your Linux box, do a man on VMstat, because this one came from, I'm going to say Ubuntu, but I wouldn't bet on it. So, and all of the formats are different, and they contain different things. So just do a man on your system to understand what the tools are telling you. Cool? Okay. Next step. We want to benchmark, right? Since we know benchmarking is such a great, wonderful technique. Yes. Okay. So here's our benchmarking process. So I'm going to create a benchmark, and I'm going to configure it, and then I'm going to baseline it to get a performance picture. And if the users are happy because the performance meets the requirements, then basically we're done. We go home. Okay? But that's not how often does that happen? Right, okay. So next I'm going to ask, okay, if the user isn't happy and the user has money, very important, I'm a consultant. Okay. Then I'm going to identify the dominating consumer, and from that I'm going to identify the next steps to follow, which we'll get into. With the profiling results, fix, QA it, re-baseline it, and ask the same question again. Is the user happy? And I go back to the top of the loop and ask, okay, are you happy and do you have money? Right. Don't forget the second part. It's important. Okay, cool. So we're going to benchmark this thing. We're going to need some things. We're going to need some monitoring here. We need observability into the system. And we need some test data to drive this thing. And this is where it gets really, really kind of fun, right? Because in production, who's our friend? Cache. In test, who's our enemy? Cache. Right? So, so we need to be careful, right? We need to have the same volume and veracity of data feeding the application, not only feeding the application, but feeding our test harness.
So you mean C-A-C-A-G?
C-H-C-A-C, right.
Oh, okay.
The one he said, C-A-C-H-E.
I was stuck on the previous slide.
Oh, with the cache, C-A-S-H. Yeah, that's important also, but yeah. Okay, but really, if you think about what's happening in modern systems, I mean, cache is everywhere. And if you don't put enough data into these systems, basically you're just going to measure cache-to-cache performance. And that's really good for getting the product out the door, but not that great for making customers happy when they finally run real data against it. Okay? Now, the reason why you need real data on both ends is because you could have like, a terabyte of data here, but if you only ever look for Mickey Mouse, then that pretty much describes your benchmark. Okay? Because it's going like, ooh, he's only looking for Mickey Mouse. Let's just cache that. And it's cached, and then it's cache-to-cache performance after that, right? And this is the really, really most difficult thing to get right. Because how you define this and how this puts the pressure down on the stack is going to affect the signal you get at the bottom. And if you get a different signal on the bottom than what you're expecting in your production systems, then you're going to go down the wrong diagnostic path. And it's actually worse than that, but I'll leave it at that for now. You can imagine it gets worse. For that reason, I only do diagnostics in production systems. I rarely will do any diagnostics in test environments. There isn't a test environment created that can reproduce a production system reliably. And you either get performance problems, so you've seen it, right? Performance problem in production. You try to get it into test, what happens? Doesn't show. So what do?
You get other bugs that are even stupider.
Right, that don't show up in your production environment. And I did this actually with a company that builds profiling tool. I gave them a problem. So I went over to their office and I said, here's a problem, let's take a look at it. And the developers started doing like stuff, and I go like, wait a second, what are you doing? And so, well, we're going to start slow, and it's like, no. If you want to test this thing, you want to find the problems that matter. You need to put the pressure on the system that you're going to see in your production environment, right? If you start like with 10 users or 20 users, and then then I'm supposed to go to 1,000 user. Basically, what you're saying is like, can the product scale down, and how does it scale up? Now, those might be important questions to ask, right? But generally, if you're trying to get it out the door, it's like, and it's going to 1,000 users, I'm going to test it at 1,000 users because I want it to break. If it's going to break, I want to break it now, fast, It's not my firstborn. I don't have to treat it with kid gloves. We want to break it, okay? I want to see how it's going to break so that at least I have a chance at fixing it. Okay. Cool. Time for a demo? See how it all works? Awesome. Okay, demo, yeah. We won't go through a full demo here. I probably could, but normally, last time we went through this full demo, it took 3 hours. So, I mean, I could if you wanted to. I mean, for me, it's like morning time, so I'm waking up. So it's might not be so good for you guys, though. Okay, let's see what we can do. Oh, look at that. Windows over here. So I have a web app here, and I'm actually doing some. No. Okay, I'll fix that. Mirror built-in retinal display. How's that? Hey, do you like my beach picture here? Isn't that cool? So in July, we run an unconference called jClarity. You can look it up. It's really cool. And that's one of the beaches we have our sessions at. Yes, they're called swim-ups. You know, stand-ups? We have swim-ups. So they're really kind of fun. You think I'm kidding, actually. It's serious. Serious stuff. Yeah. Where was I? Okay, so we have this web app, and I think it's running in the background. I think I left it running. Oh, I have JMeter running. I got some other windows here for other stuff. Whoops, that doesn't look good. Maybe I better start that again. See what's going on here. Okay, awesome. Ignore the exceptions. They're not there. Okay, so I have a test harness here. And what it's going to do is it's going to basically make a lot of web requests against this web app, and the web app is going to do stuff, and you know, and we're going to figure out if this thing is going to react well or not. So we need to know dominant consumer of the CPU. So let's bring up a CPU view. Let's see, view clear. Yeah, you didn't see that part either, did you? That was my test run before, so I think it only runs for a minute or two. So this run, you know, benchmarks are really exciting. You know, since I do a lot of benchmarking at home, my wife will come and say, "What are you doing?" "I'm benchmarking." She says, "No, you're not doing anything. You're just sitting here staring at the screen. Come here and help me do whatever." But no. We're done. Okay. It's really fun. Okay, so let's just get this thing to run, and you can ask questions while it's running, and you can watch this thing, and you can tell me what's wrong. I actually put the hardest problem in first, which is taken out, and so now we have the second hardest problem. Oh, what happened here? You gotta be kidding. What happened here? Okay, let me fix that first. That shouldn't be happening. And that was working just fine because I tested for this just prior to coming here. So what the heck is going on? Yeah, I know, found. Thank you. It's very helpful. Yes, okay, so now what do we got here? Yeah, and which file, did you happen to see which file was not found? And data.t.xml. Oh, I got it. I know what the problem is. I guess that's really weird about that. Okay. Yeah, I get that. Oh, here it is. That should not be there. Okay, gotcha. Ooh, this test is actually running. Oh, yeah, that's right. I fixed a bug just before coming out on stage, so of course it is running much faster. Okay, so ignore all that. What's a demo without a failure? Come on. This is not the worst failure I had. The worst failure I had was actually changing JDKs just before, and just getting one that happened to be leaking spring widgets, like swing spring widgets that they use in text boxes. And so I thought I was diagnosing something else. I ended up diagnosing a memory leak that I hadn't seen before. Yes, really lots of fun. Okay. Let's clear this out so we don't get confused with what's going on here. So we should be okay. Yeah, that's starting. That's starting. That's starting. Oh, this is still running. That's shutting down. Huh? File not found. Okay. Let's try it again. I'll give this a little test because it should be gone. Okay, well, here we are. Okay, so the problem should be gone now. No more exceptions.
So why is your CPU graph red at the bottom? I thought red at the top was.
Go ask Steve.
System versus
I'm sorry, you can't ask. Sorry, go ask. That's bad. That was a mistake. I don't know. I really don't know. Tim, right? That's who? Jet lagged. That's what I claim. Okay, well, you know, the 26 milliseconds doesn't seem so bad, does it? No, maybe there's no problem here. This is really good. So this falls into the part users are happy, we get to go home. Ah, yay. Okay. Moved. Okay, maybe not so fast. Not so fast. You know, sometimes things tend to go on really, really, really nice, and then you hit this threshold, and then when you've hit the threshold, it's like, you know, things go south like PDQ, pretty.
Why is that CPU load not evenly distributed?
Oh, yeah. Well, you know, that's thread schedulers and stuff. There's a paper put out by the University of British Columbia on thread schedulers, and things like that on multi-core. You should read it. You'll be forever frightened. It's
Just for real cores, it's a virtual cores, right?
Yes, that's all you get. This is it's a Skylake. If that makes any difference, but okay. That's a cool name, Skylake. Something. Okay. So by now, everyone should have gotten an idea as to who the dominating consumer of the CPU is. Okay. Idle. Anybody? Any other guesses here? There's two more choices. Who wants to state them? Okay, we've got two of the four.
Green stands for user, red for
Kernel, yes. Green for user, red for kernel. Normally I don't tell people that, but sorry, I should tell you because you don't have Google at hand, do you? You can't look it up. What's he doing there? Yeah. Okay.
waiting. It's waiting.
Sorry?
It's waiting. That's what's black.
Yeah, the idle. That's the idle part, yeah. Black is idle. Yeah, so that's the dominant color in the charts, right? So who's going to say that idle is our dominating consumer? We have no dominating consumer of the CPU. So what does that mean? Some sort of thread liveliness issue. We don't know what it is, but we have some sort of thread liveliness issue, so let's go look for it. Okay, so we can just do a thread dump. There's many different ways I could do it. I'm going to do it this way. Let's get rid of this. I'm going to introduce another tool, Visual VM, because you guys have all tried, used, heard of Visual VM? Okay, awesome. Free open source tool for those who haven't. Go look it up. It's really fun. There's a couple of guys in Prague that did a lot of work on this thing.
I heard someone say if you're using jPDM, they are charged.
No, that's mission control, and that's another discussion, but yeah. Okay, fantastic. So here's all our threads running in our environment. First off, are we still running? Oh, we're finished. So cool. With an average of 3 seconds for this little thingy. So let's try it again and fire it up.
Is a high error rate expected?
Yes. That's not high. What do you mean high? What are you trying to say? Okay. Okay, so we look at this thing, and let's just inventory the threads. So we have an attached listener, which that's JVM thread. Oh, there's a Jetty thread, BT pool. That's an acceptor, that's an invalidator, and we got 1, 2, 3. Woohoo! Look at that, 3 Jetty threads, and then a whole bunch of destroyer JVM. Can you guys see that? There you go. Reference handlers, schedulers, TCP, signal dispatchers, timers. Let's go down, RCP. So basically, you know, and when we look at live threads, I don't want to see all threads, but we have, look at that, 3 worker threads on this machine. Isn't that awesome? We have here 420 some odd users trying to use those 3 threads.
And you have 4 CPUs showing some CPU activity and 4 not doing very much.
Yeah, there's a whole, yeah, exactly. And 4 not doing anything. Okay. I need help. What's the problem? We need more worker threads. Yay, okay, more worker threads. So let's add more worker threads to the problem. Let's see if I can do that without messing up things. Yeah, this one over here. So let's just kill that. And I have this nice Jetty directory. Actually, I'll just do it this way. Yes, this is VI. Yeah. And it says, oh, max threads 5. Well, how many do I want? I don't know. I'll put in 500. How's that? No, 100, 200. I'll make it smaller later when I figure out how many threads I need. Okay? I'm glad you agree. So let's, okay, so let's kill this thing. Hopefully it'll wind down really quickly. 3, 2, 1, 1, 50. Countdown. Oh, now it gets slow. Yeah. Done. Lovely. Okay, sweep it out. New results, new test. Bang, app server start, and we have 50 threads in there, so hopefully things will go. Let's get rid of this, and up, blah, 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 blah. Okay, start our test. Let's make sure our settings hit. Oh, I didn't attach. It's not good. Okay, threads, close down, and that doesn't look good. Oh, okay, here we go. It's taking a little while. Oh, okay, so it looks like we're getting our threads. So let's look at our CPU saturation picture now. It's not really better, but let's take a look down here, see if there's what the load picture down here. So we're still, we're okay. We're a third of the way through our test and everything is looking much better. And we're getting more pools coming up over here, and a little bit of lock thing happening on here, you can see. Some weights and locks and things. There's a little chart down here to tell you what's going on. So the yellow is weight, red is a lock. Well, orange is park. And green is the good one. That means we're going. So it looks like we're keeping enough threads busy here. What's JMeter saying? So it looks like that's pretty much all we needed to do to this particular application. It's kind of boring, but anyways, if assuming there was another bottleneck, we would just go through the same analysis, see who's the dominating consumer. In this case, we can look at this and say, well, you know, we still have lots of headroom here, lots of CPU room, so we could maybe up the load and put more pressure on it and see what pops up next.
Well, you have a lot of headroom, you don't want to contention in your thread group.
Oh, you do, you're right, I do. So let's see if we can get a strategically aligned. Are we done? No, we're close to being done. This is going to be ramped down. So let me fire it up again as soon as it finishes here. And let's see if we can create some contention here. It's coming. Total should be about 7,500. 7,500. 74. Getting there. See, this is when my wife would take me out and say, okay, time to mow the lawn or something on her 89. Okay, 90. So we have 22 live threads, and yeah, what am I doing? Let's just stop this sucker. Okay, we're done. Okay. Drop. Thread group. Should I? No, I'm not going to be that aggressive. Let's just do that. Okay. And brush, clean, bang. So I just like tripled the load. Let's see what happens here.
That means you build more concurrent users.
Yes. Yes, because I'm throwing 4,500 users at this thing over a period of 150 seconds. Not a real benchmark, but okay. So, oh yeah, but we got a lot more stuff happening here now, right? Okay, let's see if we can. Oh yeah, that's just cool. I missed it. Oh, here we go again, and bang, right in the middle. Now, so I just took a thread dump. So maybe with that strategically timed thread dump, we can actually see what the contention is, yeah? So let's get rid of it. Actually, let's see what the CPU picture looks like. Still lots of headroom. Oh no. Much better saturation. Oh, this is good. Okay, that's cool. Okay, so let me close this one off here. So I can look at a raw thread dump. Anyone like looking at raw thread dumps? Just say no? Okay, good. Then I'm going to use TDA, which is another plugin, Visual EM, also a desktop thing. Let's give myself some working headroom here. I'll shut that down. Did that actually work? I almost had to reboot earlier when I was running the earlier bench. That's why I took that problem out. It was just too funky. Okay. So basically with TDA, it's going to ingest all of the thread dumps, and then it's going to put them into these categories. These categories are built by putting a bunch of filters together, and anything that passes the filter basically gets into the category. So we saw red, that's monitors. Let's look at monitors. Doesn't look like there's an awful lot going on here. Normally if there's a congestion, then what will happen is that we will see something. So maybe I just didn't get it at the right point in time. But normally if there was a lot congestion in here that I got the thread dumps at the right point in time, then it would show up in here and we could actually now investigate. Yeah, okay, so he's idle. He's idle. He's idle. So these guys are pretty much all idle. Oh, there's more of them. Oh.
Are they idle and waiting, or are they idle waiting for a thread to do something?
This is just, yeah, it's just like basically waiting to be dispatched. So when I say it's idle, it's being dispatched. But I mistakenly spoke too soon. I forgot there's a scroll bar over there, meaning we have to scroll down and look for stuff. And so it looks like, again, we're not really going to see anything interesting here. So I didn't get a good thread dump and everything like that to figure out what the congestion was. But there is some congestion in there. And so it's possible with a little bit more investigation we could get even more throughput with even better performance results. Awesome. Questions?
I don't get it. You have like 200 or 500 threads in your application. You have 1,500 or something, 500 applicants.
Yeah.
And there are only 200 listed there that are mostly bored.
Yes. So you don't get it. What don't you get?
Why isn't there more stuff being done?
Well, because if you look at how the test is written, it's actually written so that there's a workflow in there, and the workflow is throttled. So the requests are coming at the system basically not just like rapid fire. They're coming at the system where where the load is controlled, so I can understand what the transactional rate of the system is going to be overall. So that's the important aspect.
Current deliveries of jobs is not.
It's running at about I think about 30 to 40 TPS until I went to 4 times that. So it's like about 200 TPS or something like that. Okay. So yeah, there wouldn't be a lot of threads being used at that point, right? So it's because of the randomization in there, I think it ramped up to like about 60, but then it fell back, so it's undulating. Because we never really got through the startup anomaly either, right? Because normally when I run these benchmarks, I run them for 2 hours, so I really do have time to go mow the lawn. But you know, a lot of it is just you need to get the benchmark right through a warm-up period and get it, you know, basically into a stable period where things are functioning normally. Because when you start things up, you're just basically spitting stuff work, and it gets bunched up, and then you get all kinds of queuing effects, and your results are kind of like messed up until you basically get into a churn where you get into a steady state. But I don't have 2 hours to run these benchmarks tonight, so we just made them like really nice, tight, short, and we'll just take the hit of the, you know, of not being warmed up properly.
What's the most common problem you can find when you go to that kind of
Excessive memory churn. That is the most common problem that we see. I would say that 60 to 70% of the apps that I look at, and I get GC log. You get this diagnostic from GC log, and I get GC logs. People send them to me all the time. My standard joke is collecting GC logs is my hobby. So, and so I get, I think, fairly good visibility into the memory efficiency of a lot of applications worldwide. So, and I'd say that's the most common problem you see in GC log. It's just simply unsustainable allocation rates. Yeah, that's the most common problem. The most common source of high allocation rates are the less than wonderful logging frameworks that we use, and the less than wonderful ways that we log information, and our lack of understanding as to what messaging really is, the different categories of messaging, understanding when we're logging, when we're messaging, and when we're journaling, you know, what's the purpose of the activity, and then using an appropriate framework to actually to get that job done. And I'll give you this, like an average hit on logging on transactional engines is about 4x. I say one of the nicer successes I had, I went into a product company. We took their memory churn rate down from they took their memory churn rate down from 1.8 gigs per second to close to 0, which is approximately 0. The transactional rate went from 400,000 TPS to 25 million. Okay? When you find the real bottleneck, you don't get 2 and 3 percentage points in performance improvements. You get, you know, 3x, 4x. So you can get some really big numbers. Okay. You just need to find the real bottleneck. And I think one thing about the methodology is that the people who do follow it, what they find is that more often than not, it's the methodology that's helping them to find the real, true problematic bottleneck that's actually in their system, even if it's been invisible to them before. Memory churn is generally invisible. So if you look at statistics in the industry, you probably have one study done by a group, a very good group, and they said 10% of people were reporting that memory churn was actually the primary problem in their application. So, and that's a poor visibility issue. So it speaks to all of the wonderful metrics that we collect on, you know, the Graphena and all this other wonderful, nice eye candy that generally offer very little in the way of helping us to understand what's gone wrong in our systems.
Question?
Yes.
You mentioned right at the beginning of the talk about the hardware. And
Yes.
that's been a big important part of the model. I was wondering if you could comment on whether there's much of a difference or a big difference between modelling real physical hardware versus things like Docker machines or virtual machines.
Virtual machines? Well, virtual machines need to run on real hardware. That's the biggest difference. So that means that no matter, so virtual machine is like, to me, it's like another process running on the box, right? And so it's consuming the real hardware resources. My expression is you cannot virtualize yourself into more hardware. You have to, you actually have to have it provisioned that way. So I think that, early on in the virtualization game, everyone was focused on CPU saturation because this is an industry that has, I guess, CPU envy. And what they were missing was the fact that more often than not, they were just under provisioned in terms of network capacity. So very quickly what you see is that you get HP and other people manufacturing box that just will support like many more network cards than they used to, because they just realized that, okay, saturating the CPU, we're probably not going to do it all that well anyways, but it doesn't take much CPU saturation to produce enough data that we're going to pump out over a network that we're going to completely clobber a single network channel, right? And surprisingly enough, this is also another thing that this is another situation we can pick out by looking at the garbage collection logs, by using what I call proxy metrics that are actually produced inside the garbage collection logs. Our tooling will actually do the analysis, and it can tell you if you have an issue with virtualization or some configuration issue in the Linux kernel, right? We won't tell you what it is, but we will tell you that you have it, that it's visible. Okay, you need to do a deeper investigation to figure out exactly what it is. And I would say that, can I mention names? Woolworths. They were deployed like this, like 2 network cards with somebody running an Oracle database beside them, right? And so they were going to go into a very expensive tuning operation. We just looked at the GC log and said, go to your provider and see what's going on. And when they finally got that sorted out, they just popped the Oracle database someplace else, and they were fine. They were running perfectly fine. So essentially, unfortunately for me, I couldn't charge anything for that, but that's the way it goes. They were very happy afterwards. That's the main thing. Cool. Yes?
Any good tools for analyzing GC logs?
Yes, of course. I built one myself. I've been working on it for years. And it's called Sensum, actually produced by it's marketed or whatever under a jClarity brand. And so it's good for visualizing GC logs. No, if it's a jug meeting, you can talk to me afterwards about demos and stuff like that on it, but that's good. Download it, take a look at it. We have a batch version, so we're able to analyze hundreds of GC logs in one shot. The idea is that, okay, so on most systems we're analyzing like somewhere between 300 to like 2,000 GC logs. To get through 300 GC logs individually is going to take you probably like a week. And so we can batch it and run some key performance indicators over it, and so we can sort them and just basically say, look at those ones, you can ignore the rest, they're all seem to be reasonably okay. So that helps. Like I said, if I tuned more than 3,000 JVMs, garbage collectors, last year, you can imagine you need some help to do that. Yes?
Given you mentioned allocation rates and also logging,
yes,
is obviously you're going to be using lots of char arrays and so on.
Yes.
Do you have any sort of confidence that stack allocation is going to actually make a difference to this? And
no.
Potentially,
No, I have every confidence that it won't. Okay? Because stack allocation is generally reserved. Okay, so when you go down the allocation path and it's down through the allocators, it's going to make a decision. Okay, so do I rip this thing apart and stack allocate it, or do I actually have to do heap allocation? And there's a couple of criteria it's going to use to make that decision. One of them is going to be size, and generally cars are big enough that they're going on the heap, right? It's really only small objects with primitive fields that are going to be stack allocated, and they're not going to put those on the stack if you're in a, like, you know, I equals 1 to a gazillion, create this point object, right? To manage those situations, if you put them on the stack, you're just going to blow your stacks like all over the place, right? So they go on heap.
Yeah, the other two things which could potentially help would be value classes and total elimination.
Well, okay, so in the new, currently now with string dedupe, I think Jonathan talked about string dedupe a bit. But okay, so if you're using G1, after your data reaches H5, which means it's survived 5 garbage collections, then anything that looks the same, we're just gonna like basically slap it into the string table, and it's, you know, you get 1 copy unless you do something to it. So that helps. I think there's a lot of other memory reduction techniques that are going to come with value types. So for those of you who don't know what a value type is, it's basically, how shall we say, like
Structs.
something like that, yeah. But I guess the point with value type is that, you know, there's only 1 1, so why do we need more than 1 1 in heap? You know, and there's other objects that behave that way. And so what they're going to do is strip the headers out of them, just say there's only 1 of them because, you know, these are singularities anyways. So I don't want more than 1 in heap because that's just a waste of memory. And so I think there's value types are really coming along. And so I don't know when they're going to be released. I think they're on the 11 train. I don't think we'll see them in 10, but I'm not sure of that. I haven't been tracking progress. Sorry?
They're out of 10.
They're out of, yeah, they've been, well, yeah, of course they're out of 10 because the 10 was frozen months ago and they're not in, yeah, right. So yes, 11. So I was probably shifted. I'm not used to this, like, you know, every 6 months we get something thing. It's like going a little bit too fast for me. I'm used to like 10 years in between releases. While everyone argues about, I don't know. Anyways, yeah, so I think it might be 12 actually, not even 11. The last time I talked to Brian, he was making good progress, but I don't think he was close yet. Okay. Cool? Yeah, good point. But you knew the answer to that, right? You're just saying. YOW Lambda Jam. Oh, okay. You know what YOW actually is, right?
Yeah.
Yes?
Yeah.
It's an airport code for the Ottawa International Airport, my hometown. There you go. And of course the conference is put on by Dave Thomas, one of my old professors at my university. So yeah, it's
we
really
have a
fun.
CFP that's coming up at the moment, so thanks for that.
Yeah, I would love. That would be fun to get back. Okay, cool.
It's on in Mac, anyway.
Yeah, I'll consider. Yes, any other questions? Sir? Are we all out of questions? Okay.
I have one, just one.
Okay, sure.
What's the biggest performance bottleneck you found in Jeremy's code?
In which, in whose code?
Jonathan's code.
Oh, in Jonathan's code. Actually, you know, we did.
What's the biggest bottleneck?
What's the
you
biggest
found in
bottleneck we found in your code? Actually, we had to scramble really hard to get any improvements out of Jonathan's code. I don't actually even think it was really your code so much, but it was work to dig some performance improvements out of that one. It was fairly well optimized. The only thing they did is they were doing a lot of things redundantly, so we were able to pull that out into different events in their event looping. And the one way to scale is do less. So we just looked for ways of doing less, and that managed to work very nicely in that particular case. So yeah. So no, Jonathan's code is actually generally rock solid. And I'm not saying that for any other reason except for it's rock solid, and you know that. It's usually pretty good, except for that one time. No. Okay. Okay. Yes. Awesome. Are we done?
Done.
Yay. Thank you guys. Wow.